I want to talk a little bit about the written section. Key ideas, first of all. We have point charges and plates. If you wanted me to divide this unit into two, we basically did everything with point charges, and then we repeated it for this parallel plates situation. So what kind of questions can I ask in terms of point charges? I guarantee this next question is going to be on your test. This one right here, I'm going to give you two charges. They might both be the same polarity. They could both be positive. In this case, one's positive, one's negative. And then I'm going to give you a location in a straight line between those charges or along those charges. In this case, I'm over here to the right, but I would also have had no problem putting my location right here. And I'm going to ask you one of two questions. I'm going to ask you to determine the size and the direction of the electric field, and I'm also going to, I'll call that part A. Part B, I would have also no problem saying, in fact, Mr. Dueck, why don't you cleverly type part B so that your atrocious handwriting is a little better. I would also have no problem saying for part B, I'll fix that in a second. Determine the potential. Hey, Mr. Dueck, come here. There we go. Determine the potential at point P. Okay? Third thing that I could ask, determine the potential energy between the two charges. Now let's come back and let's try all this, okay? So determine the size and the direction of the electric field at point. Oh, didn't want to delete that. That was dumb. There we go. There. Point P. We use what I called, Neve, the principle of superposition. What that meant was, look, if you give me more charges than my equation can handle, I ignore the extra ones temporarily. So for the electric field between point charges, I have an equation. What's the equation for electric field? What's the variable for electric field? You may find it beneficial to have a formula sheet in front of you as you're watching along. Not that I want to focus or target anyone who seems woefully a little unprepared, but that's okay. Kelly, what's the equation for electric field? By the way, you can have a lot of fun. Maybe I've told you this. If you go out for dinner with a friend, and every time they take a bite, you ask them a question, because they'll go, okay, and then they'll answer the question, and then just wait. And then when they take a bite again, ask them a question again. You do this for 15 minutes straight, they'll feel like such a loser. They won't know why that you're doing it on purpose. Anyways, okay. Kelly, what's the variable for electric field now that your mouth is empty? E, okay? Not EP, but E. Now, there's two ways I can calculate it. How do I know that it's a point charge formula? What variable do all of my point charge equations contain in them? Have you noticed? What variable do they all have in common? I went to go see a pirate movie the other day, but I couldn't get in because it was rated R. You know what variable they all have in common? R, radius, okay? In other words, you notice in that first row on your formula sheet, point charge works for anything, second equation. Third equation, point charge. And then I think in the bottom row, there's some more point charge stuff. How do I know? R's, okay? So electric field for a point charge is KQ over R. Now, here in this question, I have two electric fields. So I'm going to find the electric field from charge 1, magnitude and direction. I'm also going to find the electric field from charge 2. Oh. Thank you. R squared. I was finding voltage. That wasn't showing very good potential. Shut up. You just got that, did you? Okay. So, good old 9 times 10 to the 9th. Charge 1, 70 times 10 to the negative 6. all over. Careful, radius 1 is that distance. Don't say 6 and don't say, what's radius 1 going to be? 10 squared. If I quickly crunch the numbers, I would say, okay, 9 times 10 to the 9th times 70, negative 6 divided by 10 squared, or 100. I get an electric field of 6,300, and the units are newtons per coulomb. Direction. So ignoring this guy, which way would a positive want to move if it could? Right there, because of charge 1. To the right. This is the principle of superposition, because now what I'm going to do is I'm going to ignore that guy temporarily. That's going to be 9 times 10 to the 9th. Do I put the negative in? I do. Neve says I do. Why is Neve incorrect? Neve, my angel. Vector or scalar? Yeah, that's preserved for posterity. Sorry, I didn't, but whatever. Vector or scalar is electric field. Direction or no direction is the electric field. Direction or no direction. So, forces and fields forget the signs. You have your formula sheet there? Look at it. Listen close. Look at it. Listen close. Forces, fields, first row. Look at it. Forget the signs. That first row, forget the signs. Got me? Yeah. Okay. So, sorry, no negative. I will decide the direction. How? Which way will the positive one move if it could? Over, what's the radius between the negative 20, charge 2, and P? 4 squared. I think I can just change a few numbers. That's a 20. Delete that, make that a 4. And I get 11,250. Direction. Which way would a positive want to move if it could because of charge 2? Left. Since they're in opposite directions, one right, one left, I'll go winner minus loser. If they were in the same direction, Kelly, I'd just add them up and the direction would be in whatever direction I'd started out with. So the net electric field is going to be 11,250, take away 6,300, take away 6,300. I get 4,950, that's to 3 sig figs, newtons per coulomb. Direction, winning direction was to the left. What else could I ask? Well, instead of saying find the electric field, I could say find the potential. Problem, most kids, when they see find the potential, they want to start doing that because they think, oh, that's electric potential energy. No. What's potential another word for? What my mom says I have. No, Peter, more specific. What was that? Voltage. Again, I have 2 equations for V voltage. Which one is the one that I'm going to use for point charges? Okay? There's 3 equations that have voltage in them. The first one on the second row, off to the right, that's the one that has the letter D in it. Yes, that's between plates. But there is also this one, the definition of voltage. I should be careful. This works for both. This works for both, where that's the little charge that you're moving, and that's the energy or the voltage that you're dealing with, depending on what you want. So I should be fussy. In the same way that the official definition for electric field, second one on the first row, works for both, for anything. That's the definition. Those are the 2 definitions. So they work for plate charges, and they work for parallel plates, and they work for point charges. Anyways, Peter, my man, you know what? I shouldn't have erased that. Let's leave that there. Please tell me that all came back. Hey, it did. You said I should use the point charge one, which is going to be KQ1 over R1. And give myself a bit more room, Mr. Dueck. K Q2 over R2. Neve, my angel, joy of my heart. Voltage, scalar or vector? Scalar. Did you say scalar? Signs or not? I agree with you. In other words, in the first one, it's going to be 9 times 10 to the 9th, positive 70 microcoulombs over 10, right? But in the second one, by the way, I forgot to nuke the little negative there. Here, vanish negative. There we go. In the second one, it's going to be, what was the charge? Negative 20 microcoulombs. So it's going to be 9 times 10 to the 9th, negative 20. In the first one, I'm going to get a positive voltage. Of 63,000 volts. In the second one, I'm going to get a negative voltage of negative 45,000 volts. Voltage is a scalar. To find the total voltage, add them up. Add them up. 63,000 plus negative 45,000. $18,000 volts right there. Okay. What else could I do? I'm going to actually add another part C. Part C. Find how much work to bring 4.5 microcoulomb. I got to write out the word micro because I don't think I have the symbol for the little mu on my word processor here. Charge from a very long distance away to point P. So let's go back here. It's asking how much work to bring a charge in to location P from a very long distance away. From a very long distance away, what do I really mean, Ellis? From infinity, right? Okay. Well, I can't use force times distance, sadly. Wish I could, but no go. I can't use force times distance, so I'm going to have to use don't think I'm starting at any. I think I'm starting and ending at rest in this case. Change in potential. Now, normally that's final minus initial, but this is why a few minutes ago I wrote this lovely definition here. I can also get potential energy by itself from this definition, which works for anything. And in fact, it would even work for a change in voltage and a change in potential. How would I get the change in potential energy by itself? Times by Q. So another way to write change in potential energy is Q times the voltage, or the change in voltage. And you know what? The change in voltage, you're starting at infinity, you're starting at 0 voltage, and you're ending it up at 18,000. It would be 4.2 times 10 to the negative 6 microcoulombs times 18,000. And I get 0.0756 joules. Double check, did I type that in right? I did. What if I was moving a negative charge in? What was the voltage at that location? What did we calculate it to be? Positive or negative? I'm meant to be really obvious. I'm circling it positive, so which means right there, a positive charge doesn't want to move there. We would have to do work, 0.0756 joules. If it was a negative charge we're bringing in from infinity, actually it would want to fall there. I would put the negative there, and what that would be telling me with a negative answer is it had lost energy, the same way as when you drop something, it loses energy. That energy could have turned into kinetic. So another question I could ask is something like this. If a negative 1.8 microcoulomb charge starts from rest at a very far distance away, what will its speed be at location P? And what I'm really saying, Peter, is in terms of gravity, what if you dropped something from the edge of the universe and let it fall? Does it want to fall? Yeah, it's negative, and we calculated the voltage at that location to be positive. Essentially, in theory, if we were at the edge of the universe, you could give it a little push, and it's going to be speeding up, falling faster, faster. Why is its rate of fall increasing? Because the closer it gets, the bigger the force. So changing force. Okay, can handle that. Oh, give me a second here. Okay, let's see if I can do this. There is a insert, Mr. Dueck. Space, Mr. Dueck. Hey, that worked. And then I can go like this. And that'll be part E. You can kind of imagine this is dropping something. Is there a change in height? Is there a change in speed? This is a job for conservation of energy. Where you can say it's starting at rest, and it's starting at the edge of the universe, so initially it has no potential energy. Which is kind of weird. You're saying, wait a minute, Mr. Dueck, I have 0 equals a half mv final squared plus q voltage final. Yeah, you do. Okay. So, Mr. Dueck, I would have negative qv equals a half mv final squared. Yeah. Mr. Dueck, I think the final speed's going to be positive. Yeah, but wait, what are you going to put in for the charge? A negative. What's in front already? A negative. What's a negative times a negative going to be? Hey, that is going to give me a positive answer over here when I do the arithmetic. It's going to take care of itself. We've seen this equation a few times before, only in this case, because I know that I have a negative here, and Cole, I know that my charge is negative. I know the answer is going to be positive. We saw this on the quiz where we said it was 2qv over m square root. Technically, I should have a negative there and put a negative in for the charge. Once again, I'm going to say, look, am I taking the square root? I know I want the final answer to be positive anyways, and we could go from there. Oh, Mr. Dueck, I would need to give you the mass. Have I given you the mass? No, if I'd been clever, I would have made this an electron or something. So I'm just going to make a little note here. Rather than continue, I would need to tell you the mass to finish this. Oops, my bad. But we could, yes? All stuff that we can do with two charges and the location. Two charges and the location. I wrote down here, determine the potential energy between the two charges. That's not two charges and a location. That's just plain old two charges. K, Q1, Q2 over R. That would tell you how much energy there was between these two charges. I'm going to skip that for now. I think you guys are okay on that. So I'm going to go yoink, delete. Okay. Here's two charges. They're equally charged particles, they're initially placed 5 meters apart. It requires 2 times 10 to the negative 2, joules of work to push one charge to a new position 3 meters away from the other fixed charge. What's the magnitude of each charge? Whew. I say again, whew. By the way, this is from the multiple choice of a provincial that you guys haven't seen yet. This one was considered fairly tough. Okay. Any suggestions? To me, there's a key word, 4 letters, that tells me how I can start approaching this. Bree. Okay, I'm going to tackle this with work. I'm not going to go force times distance because I can't because the force is changing. So I'm going to start out saying technically plus change in kinetic, but there's no indication of any speed change here. Okay. Yep. No, that's not going to work. No pun intended, Mr. Dueck. Insert. Space. Cool. What's changing anything? Okay. In fact, the work is going to be K Q1 Q2 over minus K Q1 Q2. Although, did it say, let's go back here. That's the second key. They're equally charged. So instead of writing Q1, Q2, I could really just write, except instead of writing QQ, what's a better way to write that? No, not 2Q squared. Don't be doing that. Let's double check. Did they tell me how much work? Yep. Do I know K? Yep. Do I know the final radius? 3. Do I know the initial radius? 5. You know what? The only variable in here is Q. I should be able to solve this. Might not be pretty, but I should be able to solve this somehow, I hope. Where would I go from here? Now, you could start plugging numbers in. I think I would still kind of try and get the Q's by themselves. Is there a, whoops. Is there a Q in this term? And here? It's a GCF. How many Q's would I like? 1. How many do I have on the right-hand side? 2. Well, 2 squareds. I'm going to factor out a Q to turn it into 1. When I get that, I'm going to end up with W equals, okay, factor out not Q2, a Q squared. Left behind, I'll have a K over R final minus a K over R initial. I think now what I would do is I would actually calculate that, get a number, I don't know what it is, and then I think just divide it over and square root, because they did tell me how much work. They said the amount of work was 2 times 10 to negative 2. So I could solve this. Do you guys want me to, or is that okay? No response whatsoever. Would you like me to keep going? I can. Okay, I had one nod their head. So if I were to calculate this, I'm going to say, okay, work equals Q squared. Bree, I'm going to really quickly go back to my diagram, and I'm going to go, okay, it's going to be bracket 9 times 10 to the 9th divided by R final, 3 minus 9 times 10 to the 9th divided by R initial, 5. Let me double check. Yeah, that's what it was. Final minus initial. Wow. It's that. Okay. 1, 2, 3, 4, 5, 6, 7, 8. 1.2 times 10 to the 9th. Times 1.2 times 10 to the 9th. Oh, and you know what, Bree? The work, instead of writing W, what did it say in the question? It said the amount of work was 2 times 10 to the negative 2. You know what? The amount of work is 0.02. How would I get the Q by itself now, Bree? Yeah, 0.02 divided by that there thing, and then square root. Oh, hey, conveniently, 10 to the negative 6, 4.1 microcoulombs, isn't it? I was freaking out for a little bit with that big 10 to the 9th, but actually that gave us a nice answer. It kind of reassures me that I did it right. Okay. What else can I ask you between point charges? I can ask you to find a force. Now, I probably won't ask you to find the force between two charges. That's too plug and chug. Now, between three charges, sure, but I have to tell you which charge we're focusing on. So here's a 3-charge arrangement. And it says, what's the magnitude and direction on the negative 15 microcoulomb charge? We want to find the force right there. Again, I'm going to call this charge 1, charge 2, and charge 3, and we want to find the force on charge 2. How? I'm going to find the force from charge 1 on charge 2. I'm going to find the force from charge 3 on charge 2. Now, it's true, charge 1 and 3 are also exerting forces on each other. I don't care. Didn't tell me to look at those. It wants to know how that middle guy's feeling. Okay. K, Q1, Q2 over, and K, Q1, Q3, Q2 over, I'll call it R3. Bree is dying to say, Dueck, you forgot the squareds again. Boy, I did. By the way, what was that without squareds? What was I calculating? Potential energy. And again, the problem with this unit, hope you've seen, the problem with this unit isn't actually any tricky math. We're really just doing a lot of calculator work. It's, they all look alike. Yeah. Okay. I'd also need to get a direction. Now, in the interest of time, I'm not going to show you all the numbers. I'm going to go straight to typing. So force 1 is going to be 9 times 10 to the 9th, 35 microcoulombs, 15, ignore the negative because it's a vector, right, Neve? Divided by 9 times 10 to 35 microcoulombs, yes, check. 15 microcoulombs, yes, check. Divided by 0.46 squared. 22.33. Direction. Look at charge 2. Which direction is it feeling a force because of charge 1? Now, this is not like electric field where you're asking which way would a positive want to move if it could. To find the direction on the force, we use the like repel, unlike attract routine. So, charge 1, is it repelling charge 2 or attracting charge 2? Attracting. So, direction charge 2 is feeling? Left. Repeat between the two right-hand guys. Okay. How much of this can I retype? I think I can just change the 35 to a 9. I'm going to have to insert a decimal. 0.5. Woohoo, that works. Still going to be 15 times 10 to the negative 6. And the distance is going to be 23, half as big. I get 24.24. Direction. Which way will that middle charge feel a force because of the right-hand guy? Also to the left. By the way, if that right-hand guy was negative, it would feel, sorry, to the left? To the right, right? That makes more sense to me. I was going like charges. It's going to pull it that way. It's going to be pulling it that way. And you can see actually almost equilibrium. Close. There is a spot somewhere in the middle there where the forces would exactly cancel each other out. Kind of cool. That'd be a stable point. How will I go 22.33 newtons left and 24.24 newtons right? How do I add those two together? You winner minus loser vectorially, right? Nice straight line. I would also have no problem. So, let's finish it, Mr. Dueck. Thank you. I'll call it F net. The net force is 24.24. Take away 22.33. Winner minus loser. Take away 22.33. 1.91 newtons to the right. I would also have no problem on the multiple choice giving you this arrangement here. Charge 1, charge 2, charge 3, where there was a force either attraction or repulsion between charge 2 and charge 3, a force of attraction or repulsion between those guys, and here you would have to, well, how would I add those forces together, boys and girls? Why, I would add them how? But if I do give you one like that, it'll be nice right angles. Or I would have no problem for electric field, Kelly, giving you that arrangement, because I can't have a point there. I could just have a location there and say, I'll call that location X, find the net electric field. And so you'd have one electric field that was either left-right, one electric field that was up-down, add them together, tip to tail. That would be totally fair game on the multiple choice. On the written, overkill as far as I'm concerned. Okay? What else can I do with point charges? Also, it's fair game to go backwards in any point charge equation. So, for example, if you know I would have no problem giving you the force and saying, find charge 1, or giving you the force and saying, find the radius, or giving you the force and saying, find charge 2. I would have no problem giving you the electric field and saying, find the charge or find the radius. In other words, for all of these, so in the electric field, there's 1, 2, 3 variables. Any 2, I think the third is fair game. For the force, there's 1, 2, 3, 4 variables. Geez, am I in a slump or what with this squared? Any 3 of those, find one. Same with energy, K, Q1, Q2 over R. Same with voltage, potential, V equals KQ over R. For all of those, fair game. In fact, those are great multiple choice questions, right? In fact, a great multiple choice question would be ask you to go backwards and then also tell me the polarity, whether it was negative or positive, based on what the directions the question gave you, whether they were attracting or repelling or something like that. That would be a nice way for me to give you 4 multiple choice answers to pick from. That's pretty much it for plates. For point charges. For parallel plates, bear with me. I'm going to pause the video for a second. Put the recording back on. This is the old hand cut and pasted review that I gave out when I was first starting teaching Physics 12. A lot of these appear on your newer review. Certainly multiple choice question, I have no problem giving you an electric field picture and asking you to tell me the polarity of the charges. Which way do electric field lines point? Which way are those what are those arrows there telling you? Which way, what would move if it could? A positive. So if a positive wants to move that way, this x, is it positive or negative? Got to be positive because it's repelling. This y, positive or negative? Negative. Okay, so that's a great multiple choice question. Oh, here's what I was talking about. Here's a good find the net electric field. Here you would have to add them tip to tail. You'd have a lovely vector question. If you want me to do that one later on, I will. Certainly, I've already told you numerous times you can expect to see the electric field linearly between or next to 2-point charges. Oh, which of the following diagrams shows the electric field between equal but opposite charges? Which of those are equal but opposite? Why is B wrong? Look very closely. Why must B be wrong? Ah, here the electric fields are pointing towards the positive. Well, that's not which way. So I would cross that out and say, look, I don't even know what's going on there, but that's impossible. As a matter of fact, D is wrong for that reason as well, because if you ask which way would a positive want to move, no. No. So wrong and wrong. Which way would a positive want to move if it could? Which way would a positive? Well, but these lines are wrong. So looking at C, a positive charge would also get attracted to the negative. It wouldn't get repelled away. Like if you put a charge right here, it would get repelled by the positive but attracted by the negative. This is the correct electric field lines. So I will ask you some electric field line questions. There's a bunch in your review, I think. I'm pretty sure. Let me find a picture of a parallel plate. There was one there, and I may come back to that, but hang on. Is it me, or is that almost the same question you had on your test, or your quiz? No. Sure, let's use this picture, Mr. Dueck. I was kind of hoping to find one well, to take up less paper, I want to see if I can find a nice vertical one. Give me a second. Nope. Heck, Dueck, do it this way. Plates, draw. Copy. Paste. There. A couple parallel plates. Okay. I will tell you the voltage. So what are some questions that I can ask? Well, first of all, I can say, come on. Find the electric field, magnitude, and direction. So I would give you something like this. I would say this is negative 100 volts, and this is positive 400 volts. And I would tell you that this distance here was 0.16 meters, and I would tell you that this distance here was 0.36 meters. How do I find the electric field between plates? Ah! Nothing? Gotcha. How do I find the electric field between plates? Okay, so if I'm going to find the electric field, it's going to be the voltage divided by the distance. What's the voltage here? Careful, don't say 400 because it's not. Now, by the way, 9 times out of 10, one of the voltages will be 0, and so you can just read, but every once in a while they won't, so I'm just trying to teach you, be careful. Not 400. What is the change in voltage? How far do you go if you start at the top and go to the bottom? What do you travel through? 500, yes? Okay, so 500 divided by which distance? On your test, I'll always give you both of those distances on purpose. Do you divide by how long the plates are or how far apart they are? How far apart they are. So it's going to be divided by 0.16. We would say this has an electric field of 500 divided by 0.16, 3,125 volts per meter or newtons per coulomb. Direction, because I did ask for that. What's the electric field direction? I heard someone say up, I heard someone say down. Which way would a positive want to move it? What? Why? Because a positive would move away from what? A positive voltage towards a, okay? In fact, even if this was positive 100, it's still going to move up because that's less positive than the bottom part. Relative to the bottom part, the top is negative. Relative, okay. Anyways, let's put that back. So what did you say, Ray? What, Rays? Rays. Ellis? Good gosh, am I tired? What was the direction? Up. Okay. What else could I ask? I could say if a proton is moved from the top to the bottom, how much work? How much work to move a proton from the top to the bottom? Does the proton want to move to the bottom? No. That would mean moving it closer to positive. So it will take work. Right? Doesn't suggest that we're starting or ending at anything but rest, so we'll do that. How can I calculate the potential energy between plates? Don't tell me anything with an R in it. How do I calculate the potential energy between plates? Don't tell me anything with an R in it. That comes from the definition. The fact that they define voltage as that doesn't have an R in it. I can rewrite that as PE. So turns out the work is just going to be QV, which I think we've seen a few times show up before. It would be 1.6 times 10 to the negative 19 times 500 take 8.0 times 10 to the negative 17 joules of work. I could reverse this question, Peter. I could start the proton out on the bottom and ask, how fast does it hit the far wall at? Now, in that case, I would use, hey, there's a change in height, there's a change in speed, conservation of energy. I'd need the mass. Wait a minute, I did give you the mass of a proton on your sheet. Just for giggles, suppose I started a proton right here, and I started an electron, suppose I started a proton right here and an electron right there, and I let them both go at the same time. Who would hit the far wall first? Or would they hit at the same time? Convince me. If we're talking about who would hit the far wall first, what we're really saying is who's going to travel the fastest. Hey, if I wanted to look at for speed, that would be kinetic initial plus potential initial equals kinetic final plus potential final. And I would say starting at rest and hitting the ground. But in both of these, you get QV equals a half mv squared. I swear this was from the quiz that we marked most recently. We ended up with V final being 2QV over mass square root. So Neve, you pointed out that for a proton and an electron, Q is the same. V is the same. They're going through the same voltage. But you said the electron has a smaller mass. It'll travel faster. It'll cross faster. By the way, which one gains the most kinetic energy? Well, the kinetic energy is equal to Q voltage. Do they have the same charge? Are they going through the same voltage? They're both going to pick up the same kinetic energy. It's just that the electron's lighter, so where does the extra energy go? Oh, speed, because it's got a smaller mass. Is that okay? Just doing, I'm trying to mix and match and reinforce little thought experiments here. Okay. Let me look here. I wrote one fixed charge, one moving charge. I think we did that already. Sort of, how much work to, so going back to this one with one fixed charge and one moving charge, definitely you can expect how much work to move the charge in. This, here we took it another extreme and I told you the work and we had to find Q, but if I told you Q, you could certainly find the work. Looking at my notes from previous tutorials. What else did I do a big bugaboo on? Electric field, check. Oh. Key idea, the electric field between parallel plates is uniform, is the same everywhere. So, well, this also means that the electric force on a charge between plates is constant. It means, Kelly, that I can calculate the electric force as QE. Now that equation's not blatantly on your formula sheet. That's the second equation, getting the F by itself. That one works for both point charges and plates because that was a definition equation. That was where I defined what electric field was. I said electric field was the force per coulomb, which also means that force is the charge times the electric field at that location. Oh, and remember, electric field between plates is voltage divided by distance, so that could even go in there too if you needed to. That's why plates are so nice. It means between plates we can actually even use work equals force times distance, although we used work equals QV because that was even shorter. But you could, if you needed to, go work equals force times distance. Which force? The one that I just wrote here, QE, where E is also voltage divided by distance. It looks good. 2-point charges. Find net electric field. I've done that already. Find voltage. I've done that already. So I think what I'm going to say now is, were there any questions from the reviews that you wanted me to go over that you were going, I'm not so sure? There are some, oh, I haven't done my, I like this question, I like this question. Let me do that first. I think I like number one. I think I like number one. I can't guarantee. I think it's on one of my versions of a test somewhere. I like number three. Definitely I like number four. Sure, number 6, finding the voltage between parallel, the electric field between parallel plates. Absolutely, I like number 7, I like number 7, I like number 7. Also, I could ask you to find the electric field at point P. I like number 11. Oh, there you go. Number 12. I absolutely like number 12. Number 12, example 12. I like number 12. I like number 13. I like number 14, 2 points and the electric field to the right of them. So I like number 14. I like number 14. Hopefully you're cluing in. Sure, I like number 7. Number 16, worth 7 marks. How would I do this one? Hey, here's a proton falling up. Change in height, change in speed. This is a job for conservation of energy. I'm not going to be able to use work equals force. It's going to be it's going to be change in potential plus change in kinetic. In fact, I think we did one kind of like that on the test today that we marked, test number 2, except that was between plates. Number 18 is meant to look really scary. What are they asking you to find in number 18? What's another word for potential? Scalar or vector voltage? You know what? All you need to do is go KQ1 over R, KQ2 over this R, and add. I guarantee one of these answers is if you draw vectors and add them tip to tail and do the trig, I guarantee that's also... Give me your pen. I guarantee that's also one of these answers. Okay? Don't do that. I like number 19. I like number 19. Number 19 is a nice question. A little bit trickier because it's coming with an initial velocity. To make it a bit tougher, they didn't tell you the initial velocity. They told you its initial kinetic energy. Wait a minute. Kinetic energy is a half m. V squared. I know the kinetic energy. It's a proton. I know m. I can find what V initial is and then go through the voltage. I like number 20. '21, sure. I like number 22. I like number 22. Well, 23 is another electric field question. So obviously I like it, but I've already said I like it like 5 of them. But yes, I like this one. Oh, here it's also asking for the electric potential. So electric field and electric potential. Nice touch. What's number 24 want me to find? How much work? Work, scalar or vector? They've done this deliberately as an angle to scare you. Don't worry about it. How much work was done? Initial potential to move from point X to point Y. Final minus initial. Final potential is going to be Q1 times Q2 divided by 3 times K. Initial potential is going to be K, Q1, Q2 divided by 8. Subtract them. Don't go all funky. No tip to tail. Subtract them. It's a scalar. Who cares? That question right there, moving from 8 meters away to 3 meters away, is mathematically, in terms of the physics, identical to this question right here, moving from there to there. Yes, these are in a nice straight line and look less scary, but it's a scalar. Who cares? Yep. Yeah, 27's nasty, but sure, as a multiple choice. 28, yes. Charge Q1, they gave me Q2. Sure, 30 is good. $33. 35. 36. So 37, absolutely. So here's the net force on Q2 from, so 3 charges, find the force from 2 of them on the third one, magnitude and direction. So cathode ray stuff, not on this test, okay? Will be a couple of tests from now, because actually a cathode ray tube doesn't deflect with electric plates. We really deflect them with solenoids nowadays. Well, until 2002. Thank you, Nansreen. 39 is good. 40 is good. So 44, do it, but don't freak out about it. This diagram is meant to scare you. Peter, what are they asking me to find in 46? Scalar or vector? Find, because work is going to be change in potential energy plus change in kinetic, cross out the change kinetic. Find the potential energy right there from that one, and you could just double it because those 2 charges and those 2 distances are the same. Find the potential energy right there, subtract. Don't worry about angles, no cosine law, no crap like that. It's a scalar. Absolutely, number 47, find the net electric field. Hopefully you're cluing in that I'm hoping that's a free 7 marks by now. I hope. 50A is totally fair game. Find the mass. What's 50B? B is yucky. I would have no problem as a nasty multiple choice. Certainly 50A, we did that in our homework where we found the mass of, or we found the charge. This one has 5 excess electrons, so it's got a charge of 5Q. So there's a scholarship that to me isn't too bad at all. 51's overkill. 2 protons are separated by a distance of 1.5. Okay, 2 protons separated. If one is released, it's going to repel, yes? What's its final speed? I guess we're saying how fast is it going when it gets to infinity? What's its final potential energy when it gets to infinity? You know what? I don't think this is that bad. I think this is a change in height, change in speed. This is a job for conservation of energy, I think. I don't know, maybe. So any questions from any of the homework you would like me to go over? We're good? That help? I hope, I think. Okay, let me first of all go like this.